Welcome on this President's Day. Not a holiday for CSU East Bay, though. Although I have had a lot of questions on it. According to the East Bay calendar, we have class. I'm here, you're here, we're all here. Let's have class. This week's about sorting and searching. So the lecture I'm going to give you this morning, I'll do, I think I'll do the sorting. And then all about trees will be your asynchronous lecture for this week. And it goes along with assignment number 3. In assignment number 3, you're going to do a simple, I don't know about how simple it is, but you're going to do a search algorithm in part 1. Search algorithm is going to find a bus route, a bus schedule, so you can avoid those zombies. I went over this last class, so I'm not going to spend too much time going over it, but I'm showing you what information you're going to need for this assignment. This will be in the asynchronous part for this week. Part 2 is about the efficiency of the algorithm and looking at minimum spanning trees. I'm going to have a little lecture for you on that as well. I might do that this week or next. This assignment is not due for another 3 weeks or so. I'll check that in a few minutes. Part 3 is that quicksort algorithm, which I want to talk about today. And then part 4 is on the mergesort algorithm. So mergesort and quicksort, which are better sorting techniques. So let's take a look at the analysis of sorting algorithms. Let me just double check here. The assignment number 3 that I'm talking about isn't due until March 8th, which is quite some time. So if you haven't done it yet, assignment number 1, the original due date for that was the 15th, which was yesterday. So you should be working on perhaps number 2. Number 2 is pretty easy. It's a stable matching and greedy algorithm. The stable matching is pretty easy, actually. It's not so bad. It might be new to you, though. There's a stable matching video out there that I posted to go through that, what you're supposed to do for that algorithm. And then we're up to number 3 at this point. So we're actually kind of ahead. A little bit ahead of schedule, which is good. So I can sort of slow down, I guess. Not too bad. A little announcement about next week. I will be out of town on Monday of next week. So I will be posting 2 asynchronous lectures instead of just 1. So next week you're still going to have a lecture. We're way ahead of schedule. You're not going to fall behind. Maybe perhaps you can use the time, hour and 15 minutes of your day to maybe work on assignments, perhaps. But I'll send out an announcement and they'll put a sign on the door, but just letting you know so you don't trek out here in the middle of the rain in the morning at 8 o'clock and find out there's no class. That's next Monday. So I'll make up for the missed class meeting by having some asynchronous lectures for you to watch. So sorting. Let's take a look at this. Most algorithms start out with some sort of sorting. Even the binary search, if you think about it, in order to get the list in alphabetical or numeric order, however you're sorting it, you need to sort it ahead of time. Now, not all sorting algorithms are created equal. You probably got this in data structures and algorithms, but just in case you didn't, I'm going to do a little bit of a review on the important sorting and searching this week, so you can apply it to more advanced problem solving. So sorting is the process that organizes a collection of data into ascending or descending order. Generally speaking, it's usually alphabetical type of data. It could be also numbers, though, too. Any data can be sorted as long as there's a particular order to it. So formally, you have an input, which is a sequence of numbers. The output is the reordering of those numbers in some sort of a sequence that meets the needs for the reason why you're sorting it. Given the input 6317, the algorithm should hopefully produce 1367 if sorting in ascending order, which is fairly the de facto standard. So you call the instance of the problem. So yeah, it depends on the criteria that you're looking for in terms of what order you're going to get for the outputs. So some characteristics to remember. Just gonna brush off the dust on your sorting algorithms. You want to organize the data. So you've got a collection of data, whether it be in an array, a linked list, in whatever data structure you're actually sticking the data inside of, doesn't matter. The sorting algorithm is the same. So it doesn't lend itself to any particular saving technique. So we encountered sorting almost in everywhere. For example, prices in grocery stores, highest to lowest, flights, grades, songs. And it comes up a lot in real life, actually, more so than you would think. Most people know maybe 2, 3 sorting algorithms that you use, perhaps on a daily basis, perhaps, or in your programming. Especially if you have a small group of numbers. A lot of people just do like a linear sort of some sort. Very inefficient when you're starting to look at larger data sets. So today we're going to look at the inefficiencies between the basic ones, the easy ones, which would be like the selection, the insertion. When it gets to the bubble, now we're getting a little better, but the bubble's kind of complicated to implement. It's the merge sort and the quick sort that use more of a divide and conquer type of approach to it. So the ones on the lower end of the list there, the merge sort and the quick sort, are what you're doing in the programming assignment number 3. So you're going to be implementing those two. Interesting turnout for most people thought it was a holiday today. So glad you guys are showing. It's nice. It's not a holiday. School is on today. Anyway, but you guys did miss the announcement. I won't be here next week. So next week I will, I'm going out of town and I can't get my flight back on Sunday. Well, it costs like $500 extra to come back on Sunday. So I'm like, I'm not doing it. I'm coming back Monday. So I won't be here at 8 o'clock in the morning next Monday. But I'm sure you guys won't mind. All right. So this class, we're going to learn selection sort, insert, bubble sort, merge sort, quick sort. These are among the most fundamental sorting algorithms. I'm also giving you this information on the assumption that you've seen this stuff before. Perhaps it was a long time ago when you took data structures and algorithms, but focusing on the efficiency aspects of these algorithms. A stupid approach uses up computing power faster than you might think. When I think a stupid approach is really the easiest approach, which would be, selection sort actually is not so good. Interactive graphics, when you need to have things done in a particular amount of time, the sorting might actually be a problem depending upon your application. So it's something that you do want to look into. We've got a lot of different variances in terms of sorting in millions of numbers, what that might look like. There's a wide range is the take home on that. Big range. So let's just start out with my review of the sorting algorithms. Selection sorts. All right, it's probably the easiest one to implement. You stick everything in a data structure of some sort, create a loop, go through each one of the items recursively, actually. You could do it recursively. Or you could simply just do a simple one pass and then keep calling the function over and over again. So partition the input list into sorted and unsorted parts. So you have 2 lists. In fact, the premise for most of these sorting algorithms, the easier ones, have a unsorted list and then it has a sorted list. Selection sort, exactly how it sounds. Select the smallest item and put it in the new list. So put it at the end of the sorted part. Increase the size of the sorted part by 1, and then repeat this n minus 1 times for each item that you're going to sort from the elements. So we got that original list on the top there. The selection sort would go through looking for the smallest item. Well, that's a loop. So if you get the whole list and you have to exhaust the whole list to go through to find the smallest item, then if the list is large, the efficiency is really bad. So you got a major loop, so you got a first n going on there. After the first pass, you pull the 8 out, then you pull the 23 out. You guys get the point. And then the colored section is the new list. So if people can do it inline in the same array, you could do it. Most people, if you're using an array structure for this, you're going to have 2 arrays. You're going to have the starting array, and then you're going to populate the finished sorted array. Not quite sure I would use an array though for any type of sorting feature, because what's going to end up happening there is if you do make, well, hopefully the algorithm doesn't make any mistakes, but you don't want to have any shifting of any items. So in the selection sort, you don't really have any shifting because you're going to put either start at the end or start at the top of the list and just start putting the new values in to that sorted array. You don't have to implement the selection sort for this particular class because it's not very efficient. So the examples in this lecture are C++. There's some template classes in there. As I mentioned, hopefully I've mentioned a couple of times already, you are allowed to use Java if you want. The theory is the same. The sorting technique is the same. The efficiency is the same. It's just implemented for you rather than you having to do it yourself. The manual approach here. Although there are some template classes in C++, or if you're using C, you can do pointers and stuff like that. Java's got it built in, although in Java you can't pick out, I want to do a selection sort, or I want to do an insertion sort, or a bubble sort. However, you could probably write the code pretty easily, and you can find code actually all over the internet because the sorts are done very similar to the searches. They're all done the same way. So if you've seen one insertion sort or selection sort algorithm, you've seen them all because there's no variation with that. But you can see the looping here. So we have a outer for loop and we have an inner for loop, and we have a swap going on here. So that's a lot of looping. So, and then we have a method here for the swap, and that method call counts as an end value as well. So the selection sort is O(n) to the second for all three cases, worst case, best case, everything. Therefore, it is not very efficient. It's easy though. And if you only have a small set of numbers, small set of information, and you need to get it done quickly, it is a viable solution. It's just not going to work really well for higher end applications. Okay, so another one of the not so good algorithms would be the insertion sort. Also a viable option, comes in handy for a lot of things, and it depends on the application you're trying to create or the result that you're looking for. The insertion sort is simple sorting that is appropriate for small inputs, just like the selection. So most commonly sorting technique used by card players. So back to watch people play poker or cards. People put things together. Imagine just playing cards. So if you want to remember the insertion sort, it's go to Vegas. You have to say it's for your algorithms class. Yeah. Hopefully they won't throw you out. You're not card counting. I'm just looking at how you're sorting, watching people sort algorithms, sort cards. Usually they put them together. Like I put if I had a full house, I put all the fours together, four of a kind together. I put the three of a kind together. I'd get it all sorted out. Again, the list is divided into two parts. We have the sorted and we have the unsorted parts. In each pass, the first element of the unsorted part is picked up, the transfer to the sorted start. So you're going back and forth, just like the insertion, just like the basic algorithm. So the list of n elements will take at most n-1 passes to sort the data. And there's our cards right there. So we pull something out and then we insert it in. I certainly would not use an array for this one because of all the moving. You need a dynamic data structure if you're going to implement this one, perhaps a linked list structure of some sort. Or you can actually use a tree structure. We all know that a list is a tree, I hope. And a tree is a list. We'll look at that as well this week. But yeah, we got, looks like number 7 is in the picture, but I don't even see 7 in the list here, which is interesting. 2, 4, 5, 2, 4, 5. Yep, they're moving things around, sorting them in. So in the unsorted list, the original list up here, we've got a 23, looks like we've got 23, 78. After pass 1, we take the 23 and the 78, and guess what? We switch them, move them around. And then we're going to take, after pass number one, we've got the 45 smaller than 78. So we take the 45, put it over here, 78, put it over here. So we're swapping the items 2 by 2 as we go through the list. And we have to go through as many passes as we need to in order to actually finish the list and get them in a sorted order. So that insertion sort, she sells tongue twister, sort. Also a lot of looping. Look at that. We got an outer loop, we got an inner loop. Doesn't look any better actually than the last one we looked at. What do we got here? A little better, maybe for the best case. So the running time depends on not only the size of the array, but also the contents of the array. So this is one algorithm where you have more passes depending upon how unsorted the list is. And if you've got a huge unsorted, if you have a partially sorted list, it actually would perform better. And what do you mean by that? It's like maybe somebody attempted to sort the list. Let's say you get some data and it's a bunch of passwords or something, a bunch of login informations, and you want to sort it alphabetically to create a phone directory or something. And it started out that way several years ago, but then new people showed up. They just started adding more to the list and they didn't really reorganize the list. And now you want to reorganize the list. Not a bad option for this particular algorithm. It's pretty easy to implement. So the array is already sorted in ascending order for O to the n. If it's already sort of, if the array is recursively ordered, O n to the second, the average case, we have to look at all the possible initial data organizations. So, which means we have to kind of take a look at that list. And depending upon how unsorted it is, it could affect its efficiency, which is different than our original algorithm on these selection sorts, because that one doesn't really matter because we have to go, the idea is we have to go through the whole list anyway on the selection sorts. So here we're going through the whole list, but we're not doing it on each pass, we're doing it incrementally. So by breaking down the list, we end up with a faster sorting because it's we're not having to exhaust the entire search space each time we perform an insertion. So the analysis here, the running time will be used to characterize this algorithm. We'll take a look. We just looked minutes ago, actually, at the insertion sort. Where it's the longest running time, this is the upper limit on the algorithm. It's guaranteed that the algorithm will not be worse than this in terms of the definition of the worst time. So sometimes we're interested in the average time. The average time is actually a pretty good indicator of what it is we're looking at. But there are some problems with the average time. Difficult to figure out the average time case. Is the average input. Yeah. With this particular insertion sort, it's hard to figure out what an average would be because of the data and inconsistencies or fluctuations in how badly unsorted the data is. All right. Are we going to assume that all possible inputs are equally likely? That's a good question. In fact, the most algorithm average is the same as the worst case usually. All right, so let's get some better sorts. Now we're moving up the chain. We're moving up the food chain of the sorting algorithms to the bubble sort. The bubble sort is it's nice in concept. We're repeatedly swapping adjacent elements that are out of order. So, and in doing so, what ends up happening, and the reason why they call it a bubble sort is because the lowest numbers, the first numbers, they start floating up like bubbles. Yeah, that's why it's called a bubble sort. So you sort pairs of elements that are far apart from each other, then progressively reduce the gap between the elements to be compared, starting with the far part of the element and moving to move some out of place elements into position rather than the simple nearest neighbor exchange. So it's a generalization of another algorithm that used to be called the shell, well, still is called the shell sort. So, all right, so you're swapping, very similar to the insertion, moving items around, but here you're going two at a time. So we have 23, 78, 45. Oops. And eventually, after 1, 2, 3, 4, 5, 6, about 6 iterations through, and hopefully you're getting the idea, there's a lot of iterations through this, because you're not sorting the whole list in one shot. You're taking the whole data set and you're going 2 at a time. So by swapping things, we slowly bubble up the small so we can get the order eventually. You don't have to do the bubble sort in this class either. It's just a quick sort and the merge sort, which is coming up next, that you're going to probably be interested in. So here with our bubble sort, we've got lots of looping. So we have a for loop, another for loop, and a swap, and some pseudocode for it. So we need to swap as many times as we need to swap until the entire list is sorted. Depends on how large the list is in terms of how much swapping is going to go on. We're looking at a very similar algorithm efficiency as the selection sort and the insertion sort, very close. In fact, the sorting algorithm, which sorts elements by swapping adjacent elements, can be proved to have O(n) to the second average complexity. So it's looks very similar, looks extremely similar to the efficiency. So it's a matter of preference. If you're picking out one of those lower end, and I say lower end, less or efficient algorithms, it's about ease of implementation. And sometimes the data just lends itself to a particular algorithm, depending upon the nature of how the list is partially sorted, or I don't know, not sorted at all. Any sorting algorithm which sorts elements by swapping adjacent elements can be proven to be O(n) to the second. It's just the performance that you're guaranteed to get. To understand this consideration, if we look at this array, the array has 3, 2, 1. And then we look at the 3 inversions to do it. So we have the 3 and the 2, the 3 and the 1, the 2 and the 1. So we have to get all the combos in there. So an inversion is defined as a pair. And we're looking at the pair, and then noting that the single swap of the adjacent elements can only remove one inversion. Thus, the above example, we need 3 swaps to make the array sorted. For an array, that's a lot of swapping. So we know that if we want to move things, we have to move them over through looping usually. So generalizing this, the array of n elements can be C n comma 2, which is the pair, total pairs, where C represents the combination. So it depends on the number of combinations and the number of pairs in terms of how much looping is going to go on. We can assume that on average, the half of the pairs are inversions. So the average number of inversions is n times n minus 1, so over 4, depending upon, yeah. So each swap of the adjacent elements can remove a single inversion, theoretically. So, but the inversions overlap. So although we have eliminated one, it might cause another inversion to occur. So anyway. So recursive insertion sort. So what you're going to find is most of the algorithms themselves are greatly improved by using a recursive solution. And then also, obviously, getting rid of the array concept and using a linked structure instead, or a dynamic data structure that can change easily without too many swaps or moves. So a good practice of recursion. So we recursively sort A, 1 and minus 1, and then insert it into the new sorted array. So we have the insertion cost as well as the sorting cost. If we do it recursively, we can cut down on some of the costs. So what you're going to be doing for assignment number 3 is a recursive solution on a quicksort and on a merge sort. I'm going to talk about those in a few minutes. But yeah, it's just kind of a sample looking solution recursively. So to sort a list, if we have a 5, 2, 4613. We use the insertion sort. What we're looking then, and we're pulling out, we have 3 inversions, 1 inversion, 6. So we pull out the 4, 2. So we reduce down the number of inversions as we get recursively closer to the sorted list. And again, we're starting with a an unsorted array or unsorted list, and then converting it to a sorted list. So that we can see the time complexity of the recursive solution to sort it. We recursively sort it, gives us an O to the n time complexity. So, all right. There is an algorithm called a fast algorithm. Not very popular, but it is out there. It does use it. So describe an algorithm that given a set S of n integers and another integer x, determine whether or not there exist 2 elements in the S whose sum is exactly x. Well, brute force. How is it fast? Well, it's sorted by maybe a binary search, because we have to search and sort to find the value that will sum to S. All right, so those are all of the inefficient sorting algorithms you probably have heard of, maybe you've used them. Hopefully you got introduced to those in data structures and algorithms back in the day. If not, they're pretty easy to learn. Most of them can be implemented in Java quite easily. And the core libraries don't actually have the lower end, the insertion. What I mean by libraries, I mean is that the util package doesn't actually, unless they've changed it over the years, never used to actually incorporate that. However, you can get a quicksort, you can get a mergesort actually out of the util package. You may also need to install a library to work with those higher end sorts. All right, so the reason why these are better is because they do a divide and conquer approach to it. So, which is a core fundamental issue that is covered in this class. It's divide and conquer. So what do we have here? Is one of the 2 important divide and conquer sorting algorithms. The other one is the quicksort. So in the assignment, I think I had it up. I thought I had it up. Let's just refresh my memory so I am not misquoting here. Yeah, part 3 does the quicksort, where you're going to do a recursive algorithm. So having smaller pivots gets, actually I even described the algorithm here too. So take the last element in the list and call that the pivot, and we're pivoting around it. So everything that is smaller than the pivot gets put onto the left, everything that's larger gets put onto the right of the list. And then you call this quicksort on the left and the right list independently. So you can do it recursively. If you actually were using threads in Java, you can actually have them both running at the same time as well in parallel. After those 2 sorts come back, you concatenate the sorted list with the left and the pivot, and then to the right in that order. But concatenate or put the list together. The base case is when you have a list of length 1 or 0, where you've just returned the list that was given to you. So once there's no more to sort, the algorithm stops. Write a program to sort elements of an array using the quicksort. Oops, using quicksort. Oh, there it is. The word got split. Use recursion in your solution. Ideally, the program should be written in C. However, it does not need to be written in C. It can be written in any language that you want, but you can use any programming language, yeah. So in here, by dividing and conquering, you are splitting the data set in half, or multiple parts actually, but not with this one. But in other algorithms, you could actually make multiple parts of it. The mergesort, by the way. This one only has 2 parts, very similar to the binary search. Or binary sort, I should say. And then I got the merge sort. While I'm here, I'll just go through this one again. It works by recursively dividing the input array into two halves until each half contains only one element or is empty, and then merges the sorted subarrays back together to produce the final sorted array. Again, you're going to write a program. Now, when it says write a program, just write a function that does it recursively. Send the function, write a main that just sends the function a unsorted list, and then just print the sorted list to the screen. It's as simple as that. You can even write it in one program if you want, and just put a little menu option there. You know, you press 1 for quicksort, 2 for merge sort, or something like that. Or better yet, just have it run the quicksort and then have it run the merge sort. So you can combine parts 3 and 4 together into one program with just 2 different functions, recursive functions that are sorting with one of each of the techniques. Why are you going to do that? It's because it's not really for torture or anything like that. It's because it's good practice to actually be able to implement, especially these 2 algorithms. I would not bother implementing the other ones, the insertion or the selection sort, because they're super easy, but at the same time, they're not going to be your best solution. So, all right, so we have a recursive algorithm. We divide the list into halves. Take the list, divide it in half, sort each one of the halves separately or recursively, and then merge the sorted halves into one sorted array. So then the next big old question is then what do we do to sort the halves? Because this really isn't actually doing the sort on the halves. It's basically providing the mechanism to divide out the data set into smaller manageable pieces. So you could do an insertion, a bubble, a selection. You could do another algorithm on each one of the subhalves. And that's completely up to you in terms of what kind of sorting you want to do. So we find a pivot. In this particular case, we're going to pivot on the 1. So we put 3, 6, 9, 1 on one side and 5, 4, 7, 2 on the other side. And then we take and we divide out again by the pivot. So now we have a division between the 6, 3 and the 9, 1. And then we take the 6 and the 3 and we divide it out. And then we merge it together. So we switch the 6 and the 3 here. I guess you can consider that a bubble, maybe. I don't know. And then the 1 and the 9, same kind of concept. It's in the wrong order. So we put the shortest one on the left, shortest, larger one on the right. So we're really doing sort of a binary left-right selection here. May also be considered a variation of the selection sort. But the differentiating part of this is the merge. It's the dividing and merging together. Now, classic mistakes on this one is to merge it in the wrong order, or to flip the order, or to forget to merge a piece in. Because we have this divided out, well, we could take a larger list, divide it out into even more subparts. So we could take a list of 50 numbers and go 25 and 25, and then sort the 25s. Or we could just take the whole 50, find a pivot point, find another pivot point. It's the same amount of divisions, same amount of work, but one of them working with a set of 50 is going to be a little bit more complicated if you're doing it manually, of course. If you're doing it recursively, I don't think it really matters. So it's about the same because of the merging. If you divide it out into 2 or 3 or 4 different subparts, or if you keep the 50 all together and then divide that out and merge it together. So anyway, long story short, very effective. Works by dividing the group out and merging the subpieces back together. And there's a couple of variations of this in implementations. But for the most part, here's a sample C++ function where we've got a maximum size that we want to work with, maximum number of elements in the array. We've got a merge that's going to take a function call that's going to take a data type of an array is going to take the first, the middle, and the last. And we just keep sending it to the function. So the beginning of the subarray, the first element, the middle element, the last element. And basically doing the same as before. We have a sorted array, and then we have an unsorted array, taking the unsorted and turning it into the sorted. Now, these examples, again, are working with an array concept. You don't actually have to use a physical array. In fact, here it doesn't really matter, especially if you're starting with a blank array, because you could take sub pieces of it and merge them and add them to the array at different times. So, and then finishing off the first array, if necessary, a loop to go through the temp array and create the new array out of it by putting the pieces in there. So that's some more sample code for you. I don't believe there's an actual merge sort in the Java util. If there is, you're lucky. If not, it's a pretty easy function to actually write. And you can use this as a basis. So you do need to keep track of those three pieces of information. So here's a little bit of analysis on it, a little bit better. So to solve it using substitution, we can essentially reduce the time it takes to actually sort it by separating out the problem into smaller problems and then adding up each one of the smaller problems to get the larger time that it took. So, and if it can be done on a the merging step, which is a linear time. If it can be done on a dual processor system where you can run multiple threads simultaneously, sorting through thread is using threads for it is a pretty decent solution. You do not have to do that for the homework assignment. You can just write a simple Java or C++ function or C, and then call the function from a simple main. So here's our merging step. So extra time for the merge operation that needs to be added in as well, because once we get our subparts, we still have to put them back together. So, and hopefully our subparts are sorted so that we have a clean, we have a clean break in between the parts. So when we put them together, the list is sorted in the proper order. I'm not going to run through all the steps of the merging, but there's a lot of merging in that example. So here's an example then of applying the merge sort to an array where we've got our starting numbers. And the sorted sequence, this is going backwards actually, going back from the sorted sequence to the unsorted, the initial sequence. So if we look at, I guess it could look from bottom up instead of top down. We take and we put in our merging parts for two at a time into the, well, we find the pivot in the beginning, which is the 7, I believe. So in sorting it, you see that there's a lot of merging of the subparts. So we have individual subparts to begin with. We have 1, 2, 3, 4 that goes into 2, that goes into 1. So the additional subparts are what takes the most time. Depending upon how many pieces you've broken out of it, putting them all back together may not it may not be worth it in terms of like separating it all out. So anyway, you'd have to play around with it to see how much it is, and also try it on different data sets. But this particular case, the data set's not going to matter. So like the merge sort, the quick sort is also based on the divide and conquer. It's another good one. It uses a technique somewhat opposite manner. So as all of the hard work is done before the recursive calls take place. And the other one, the recursive calls are doing your, finding your pivot, finding, sorting the subparts of the list and then returning them back to be added together. So quick sort, what I'm going to do here. First, select a pivot element, very similar to the bubble, to the merge sort. Then partition the array into two parts, so elements smaller than or greater than or equal to the pivot, which is very similar to a binary type of technique. Then sort all the parts independently, recursively. Then combine it together in a simple concatenation. That's actually a nice YouTube video that kind of shows you a simulation, how it works. In fact, what you could do if you wanted to, there's so much multimedia graphics out there these days. All you have to do is go to YouTube, type in quicksort or mergesort, and you can see a nice little graphic display of what it's supposed to look like. And it's pretty easy. Well, both of the implementations are pretty easy to check. All you have to do is look at the resulting array and go, is it sorted correctly? And if it's not, probably there's a problem with your logic in terms of the recursive calls, or maybe in terms of merging the pieces together. So for the partition, so finding that pivot point doesn't necessarily need to be exactly in the middle, but it should be. So partition places the pivot in its correct place within the array. So we have section 1, we have section 2, and everything that is smaller than the pivot, everything is larger than the pivot or larger than equal to the pivot above it. So arranging the elements around the pivot generates two smaller sorting problems. Sort the left of the array and then sort the right of the array. So, and then use the smaller sorting problems are solved recursively. The biggest sorting problem is also solved when you, so the sum of all of the smaller parts is equal to the big solution. So that pivot selection is key. So which array item should be selected as a pivot? Somehow we have to select a pivot and we hope that we will set a good positioning for it. Well, the pivot selection is going to determine how large the sections are and what kind of sorting we're able to do. If the items in there are arranged randomly, we choose a pivot randomly. So most people pick something in the center, but it doesn't actually have to be in the center. Could also, there's a variation of this where you can select multiple pivots. Depends on what you're trying to accomplish. So we could choose the first and last element as the pivot. It may be a good positioning, it might be. And then we can choose the middle element as the pivot. Most examples, you see the middle element being selected. So you can combine, so combination of the above to select the pivot. In each recursive call, a different technique can be used as well. So as long as you're remembering what logic you're using for it, the pivot selection is very adjustable. So you could play around with benchmarking different pivot positions and seeing which one is yielding better results. And generally, past the accuracy, you want to make sure, obviously, that it's actually doing the sorting correctly. But beyond that, you are looking at other characteristics for efficiency. So here's the initial state of the array. And we could choose the first element as the pivot element. Or we could choose the last one. We don't know how badly sorted the array is. So it could be that the middle doesn't have any less or more significance than either one of the ends. Or maybe just do a random. You could actually just create a random variable and just randomly select a pivot. So there's the first element. We've got our first unknown or our last element. So moving the array. So the first unknown into the S, which is going to be the sorted array, by swapping it with the array, the last one, maybe, and then incrementing both the last one and the first one, or the first unknown one, or swapping. So, and then moving, so incrementing it. So as long as we're moving in the same order, we're being very careful to catch all of the elements in the list, then it's not really that big of an issue in terms of where the pivot actually is. So we have a lot of iterations through this one where we're choosing, I believe this one is choosing the last element for the pivot. And so we're pushing things to the left or to the right, depending upon, and we're going sequentially through the list to analyze each item to figure out whether it belongs on the left or the right. So it does require you to go through each one of the elements as well. So we could do a partition function. So to find the pivot, we can put the pivot at the first position and then recursively move the pivot to an ideal location, or we could just blindly just start with a pivot location and not analyze how effective it is, whether or not there's a better pivot. In some cases, there may always be a better pivot. And so if we're willing to just use the concept of it, then it saves us from having to do a lot of calculation. But we don't want to just spend a lot of time trying to figure out the pivot or have a function that's so complicated that the pivot comes back the same pivot each time, even with the sorted or characteristics that are occurring. So, all right. The quicksort analysis. So what do we got here? So if we always select the smallest or largest element as the pivot, which is another choice, we'll not be able to divide the array into smaller size partitions. That's why it's like a random pivot might actually be more effective. In that case, the complexity of the quicksort can be defined. And then it gives us O(n) to the second complexity, which is the worst case, and our partitions are equal sized. We could have a better, if the partitions are equal size, we're going to have better efficiency, same as the merge sort, which gives us O(n) log n, which is the best case. So on average, the quicksort has been proven to have O(n) log n, so it's better efficiency based on alternatives because of problems with good and bad partition selections. So with quicksort, one of the big issues is that pivot selection. So that's something to look out for. Therefore, this is the most popular sorting algorithm. Yep, quicksort, I would say, is probably the most popular. So it's also no need to have extra time like the merge sort to actually put things together. So it doesn't require. So quicksort would be the first choice, merge sort would be the second choice, and then one of the other ones would be something to consider for smaller groups. So in the C or C++ language, I mentioned Java so far. I'm kind of leaning towards that one, only because it does a lot of more automation, takes a lot of the problems out of it. However, no language itself is going to actually give you these algorithms already implemented, unless you get into third-party libraries. But in C++, there are actually more templates and more help for it than you do have in Java. So you can implement quick sorting algorithms yourself. You can also use existing implementations. You see the function quicksort. Parts of stdlib implements the quicksort algorithm. So there's a quicksort. And then you can do the standard sort, which is part of the algorithm header that implements a mixture of quicksort, heap sort, and insertion sort. We're going to look at the heap sort in this class as well. We start looking at heaps and maps and things. So yeah, many sorting algorithms in comparison. So feel free to venture out and look at different programming languages when implementing those two. And the idea is to get yourself versed or more familiar with the actual recursive parts of it. Okay, also for this week, we have trees, searching and sorting. So let me just take a look here. We've still got about 15, 20 minutes here. I can look at graphs. Multi, let's do multi. Is that the one I'm looking for? Yeah. Multi-way trees. You're going to get a binary tree implementation. What I'm trying to do is show you ones that you may not have gotten. And this is not chapter 12. This is from a different book, actually. So this one that I just loaded up is a nice little quickie multi-way search tree. Although it says it has 82 slides. I'm not going to go through each one of these slides. I'm going to basically talk about the algorithms or the tree structure actually at this point. So 2, 3, 3, 4, 5, 6. So phone directories, dictionaries, and then all of these algorithms actually have real life applications to them. So everybody's familiar with the binary tree. And if you're not, the asynchronous lecture for this week is going to definitely brush the dust off of your memories of that. So binary tree, 2 nodes. Each parent has 2 children, a left and a right. And it's theoretically sorted. And it's sorted with a lower number on the left, higher number on the right, in ascending order. We have complete binary trees or balanced binary trees. We have, which brings up AVL trees, which are nothing more than a balanced binary tree. And we have sply trees, which is another form of a balanced binary tree. So that category is done, generally the searching on those trees and the creation of the trees is done recursively because we know the pattern, we know the order. But sometimes we have data that doesn't fit into any of these tree structures. And that's where we come in with the multi-way trees. Multi-way trees can be used for searching. We have a nice example of the multi-way tree, and that would be the dictionary. When you go to a dictionary in the old days, probably have not seen one in years. But it's usually A, B, C, D. We go to A, we can see, apple, apron, across, and all the words that start with A, B, C. That's an example of a multi-way tree. Because it has each node would be a parent, which would be the alphabetical characters. And then in each parent, we have any number of children, and it's generally unknown. And unlimited. We can stick as many children as we want in there. So nodes that contain 1 or 2 items, and then the nodes of k items has k plus 1 children, all these are on the same level. So it's a very flat looking tree. So we have a 2, 3 sorted here with 18 items. So we have, instead of 1 item in as the root, we have 2 items, which is why they call it a 2. So you can actually have a 3-way tree as well, or 4-way tree, but then that gets a little confusing. So what we're looking at then is organizing the data for the particular application that we're looking for. In this particular case, we have things that go in between. So we have a 20 and an 80. So this is the parent, or the actual root of the tree. And then we determine the left, the middle, the right, and this would create a 2, 3 structure. So we have 3 children levels with at most 2 in each one of the nodes. So 5 is smaller than 20, so it's on the left. 30 and 70 are in between 30 and 80. 90 and 100, well, those are bigger than 80. So then when that same concept goes all the way down to the leaves can actually have 2 as well. So at most we have 3 children and we have 2 parents. And you want to put them in the same bubble together because they belong to the same bubble. Where people try to get lost, well, people do get lost with this, but if you take the 80 and the 20 and you separate them out into 2 separate nodes, but you put them at the same level, and not the same because you don't have the same children. These share the same children instead of having them separated. So it's a little bit more efficient in terms of your ability to organize the data. And you can put a lot more data into a smaller tree this way. So updating the tree. So just like in the binary, we've got an insertion, a deletion technique where we want to maintain the integrity of the order of the items in the tree. This particular tree is unordered. We don't have it. It's not in a ordered fashion. It's an unordered. So if we put that into a list, it would not be an ordered list, as you could possibly see, unless we're reading it from left to right, and still it doesn't hold true. So So for the insertion, you find the appropriate leaf where you're going to insert something. If there is only one item, just add the leaf. So in this particular case, if we're inserting 23 and we're inserting 15 in here, if we're inserting 3, we're just going to put the item in. So this one can take at most 3 items. So we have a 2, 3, 4, because the 3 would actually go in between in terms of its order. If there's no room, you move the middle item to the parent, and then we split the remaining 2 items among the 2 children. So this one had 15 and 23, I believe. 23 got added and 15 got added to the bottom 2 nodes. So we have a 10 and a 25 originally. So if we add to the bottom, and then they can bubble up to the top, depending upon the next nodes that we're putting in. So yeah, adding the nodes is pretty easy. Inserting in the middle, we can move the 3 up to a parent, and then we have a 2 and a 4. It kind of looks like a binary tree at that point, but it's not. So it does have some qualities that are similar to a binary tree. And then we are done with the 3 and so if we run out, because at most we can only have 2 items per node, we can combine, let's say, the 3 and the 5 to put it together. So we have the 2, which is less than 3, 4, which is in between 3, 4, and 5, and then 10 and 15, that's above it. So it's pretty quick and easy to implement insertions. As the tree grows, it can grow at the root. So inserting 45, we put 40, 45, 50. Well, we got 3 items, which means we got to move one up. To move one up, get rid of this. There we go. So we find the spot where we're going to insert something. We insert it, and then we fix it so it's got a 2, 3 format to it. So 2 parents, 3 children. So here we have 45, which is going to be moved up, which is going to be moved up. So the 45 actually ended up at the top for the root, and the 30 got separated out. The original one had 30 and 70. So to delete it, if the item is not in a leaf exchange with the order successor, if the leaf has another item, then remove the item. Example, remove 110, insert 110, remove 100. Let me look at the graphic here, because that doesn't make any sense. So if the leaf has only 1 item, but the sibling has 2 items, then redistribute those items. So here we are removing 80. So step 1, exchange 80 with an in-order successor. So we have 80 down here. This original tree had 85. So we find 85 that comes after 80. So we put 80 in, and then 85 got moved up because it was, you can't put 3 items in the parent. So that got moved up. And so we do have a particular order that's happening here. And then remove, to redistribute it, you're going to remove the 80. And the 80 is going to be redistributed back up to the higher node. So it's hard to really just see these examples with the screenshots that are presented. However, you can get them, you can get the idea of it. And no, you will not need to be implementing 2, 3 trees. However, they do come in handy for particular solutions to problems when the data doesn't lend itself to a binary tree. So some more removals. Here we could remove 70, swap 70 and 75, remove, and then remove the 70. So we can merge the empty node with siblings and join the parent. So here we have siblings of 95 and 110 can be separated out and then redistributed. So what we're looking at here is putting out the 95. So anyway, so you could possibly see without really going through the steps that clearly. There's a lot of rotations, a lot of moving. So from an efficiency point of view, just to put something in or to take something out, it's not quite as quick as the binary tree. The binary tree actually has a little bit faster insertion deletion time. This here has a lot of movement and it has a lot of redistribution and a lot of changes. However, the data itself can be presented in a more concise way. So new tree, for deleting the 85, it will shrink the tree. So it's adjusted again. So shorter tree for a 2-3 might be existing. So I'm not going to go through all of the insertion and the deletion, especially when you don't necessarily need to do it for this class, but trying to give you an idea about what that looks like. And so you can possibly see it's not efficient. So perhaps you can see, I don't know, lots of moving around. In fact, there's a lot of variations of the 2-3 and a lot of theory behind it. Can also be solved recursively. In fact, all of these tree problems can be solved recursively. So we have the size properties of the nodes that have 1, 2, 3 items. Every node except for the leaves has size +1 children. So when the number of parents go up, so do the number of children. And we'll see in a few minutes. This is a 2-3 that we started with. You could do like a 3-4. Would also be another variation of the same concept. So this is the depth property, all leaves that have the same depth. So the insertion of doing the search for the leaf, you encounter a full node, you split it to make it easier to search. So here we have a 3 now with 4 children. So it's a 2-4. So we've got 3 parent, 2 at most 2 children. It doesn't have to be 2 children. You can have 1 or none for that matter. But now you have 1, 2, 3, 4 spots. So it can be less than 10, between 10 and 45, between 45 and 60, or above 60. So you could possibly see how that transforms. And obviously, if you put on, again, another parent, so you'll have a 4, 1, 2, 3, 4, then you're going to have 5. So you're going to have +1 on the children. So. And again, inserting, let's say 38 into this tree. 38 is coming in on the 25. So you find the spot you're going to insert it into, very similar to how you would do in a binary tree. Find the desired location, insert the node, and here no moving around was necessary because the number just fit in correctly next to the 25. Inserting 105 kind of worked the same way on the 100 that was on the left hand. So we have 105 that we're going to put in here, which means this is going to break up. So we move the 70 out, and now we have the 100 and the 105. And then the 90 got moved up so that we could have, we could distribute the weight to balance it. So removal. As with the binary search tree, we place the node to be removed in a leaf. And then if the leaf V has another item, we're done. If not, we have an underflow. So if a sibling of V has 2 or 3 items, we transfer those items. If the V has 2 or 3 siblings, we perform a transfer. So if the V has only 1 sibling, it's pretty simple. We have a single item, we drop that item from the parent to the sibling. I mean, it would be nice if all the removals were at the leaf level already, but they're not. So this might create an underflow of the parent. So we percolate, move it up, the underflow. So we're basically moving things from the leaf up to the root and then finding the location where it's sitting balanced. So in this case, we'll discard the tree and it'll shrink the tree. All right, so we want to remove the item 15. That's pretty easy. We just take it out. That one's going to work. It's gone. Drop item from the parent is going to come down to here. So we have the 620. The parent was 20. So now we drop it down. We're going to basically balance the tree because we're a little lopsided there. And then fuse it. So we have the 620 is going to go up to the 60, which is this guy over here. And he'll take 3. And then the 35 is still up there as the original parent. And then drop the item from the root. So the 35 and the 60 go together. So what we're trying to do is create the shortest depth necessary to fit all of the items. And what we want to do is fill up the nodes. So we have 2 in each parent, ideally, and then 3 children would have 2 in them each. Shorter the depth, easier for searching, smaller search space. So it's a little bit more efficient that way. So that's the balancing technique for this type of tree, which is different than what we would do to balance, let's say, a binary tree. In a binary tree, what we're looking at is theoretically trying to get all of the nodes at the same depth. So the height of the tree is pretty consistent. Here, we're just trying to reduce the height of the tree. So. Okay. Both the 2-3 and the 2-4. So they should really call it a 3-4, but it's a 2-4. Make it very easy to maintain the balance. Well, because that's the goal of it. Insertion and deletion is easier for the 2-4 tree. The cost is waste of space in each node, also extra comparison inside of each node. Does not extend to binary trees. So binary trees are unique in terms of its balancing technique, which is different. So, and then we have these red-black trees. So red-black trees, we have a root is always black. So we have a bunch of rules. So we have a bunch of rules. We have a tree. Looks like a binary tree, kind of, sort of, which doesn't have the 2 in the parent or anything like that. And we follow the rules and we slap a color on there. And then we're balanced when we have a red, black, black, red. When we have certain color balance, so we never have like 2 reds together and 2 blacks together. We have various different patterns. And when the patterns are maintained, then we have a tree that's more searchable, that's, quote unquote, balanced from a red-black perspective. External property, every external node is black. External nodes are the null nodes as well. Internal properties, we have children that are red and also black. And then depth properties, all external nodes have the same black depth. So why do we care about the red-black? Again, we're trying to make a tree that's balanced in a particular way to make it more searchable. So red-black tree, here we have a black depth of 3. So black goes down 1, 2, 3. So the depth of that tree is 3. So which means we have to maintain 3 for the black as well as for the red parts. So we're going to do an insertion then. So we find the external node, same concept with all of these trees. We find where we're going to put it. We insert the color node red. So every time we do an insertion, it always starts out red. And then we adjust the colors to match the pattern and the rules. So no black depth violation, but may violate a red-black parent-child relationship. So let Z be the inserted mode, V is the parent, and U is the grandparent. If V is red, then it must be black. So we do color adjustments. So red child with a red parent. Parent has a black sibling. So these are the insertion nodes that are coming through. And then we have 2 reds together, which is a problem. So in the red-black combination, not to go through all of the tedious insertion, deletion, and all those steps, but what we're paying attention to in this particular case is the color of the nodes. And the color of the nodes is gonna help us with the balance of the tree, essentially. So we have a rotation that's gonna work with a Z middle key. So the black height does not change, but we don't have a red to red anymore. So what we don't want is two colors that are the same together. So if we break it out, then we have the Z with the V and the Z with the U instead of the Z and the V being at this level. So we're moving the Z up one level and the W got moved down a level. So we can sort of see that rotate. So again, we have the level of 3 on the black. So we maintain the original level. And then color adjustment number 2 could be done with the U, the V, the Z again, where we're going to rotate it. But the V is the middle key. So it comes out similar with the Z's on the bottom and the two reds separated. And then we do recoloring. So the red child, the red parent, the parent has a red sibling to it. Well, that's going to be a problem because we have two reds together. So initially, when a new node comes in, it's red. It's always red. It's always going to be, we're always going to have this problem. We're not always going to have this problem, but it's likely that this problem is going to exist. So, and this coloring, this red and this black coloring can be parameters that you're putting in the node. Just like when you put like values, just a field in a node, it just says color or just says, it indicates what it is. And it's a technique to organize the tree, essentially. We don't necessarily need to do it for the data. It's for the balance. So the red black may move up. So here we have a V down here and a Z down here. So we moved the U, we swapped the V and the Z so that the colors change now on the V to black. So now we have a red-black combination there. So for the insertion, so we insert 10, 10 always comes in, and we're going to start with a new tree here. 10 is always, it's going to be red. External nodes are not shown here. And then when we add a new node in, 85, for example, the 10 turns to black instead of red because we have a key. So when you're creating the function that adds the node or inserts the node, you can do the color adjustments on it as well. And it gives you some extra parameters that you can use to solve problems, to, I don't know, analyze the data that's in the tree with looking at the color, the construction of it. Because the number of nodes of each color is going to tell you some information about the tree. So not necessarily for searching, but for balance. So rotate it, change the color. So now we have a 15 with two reds. Insert the 70, comes in as red. Well, we have to change the color of the 85 to red to black. We can have more, we can have two blacks touching each other. So this is okay. We can have a black children from a black. It's the reds that we don't want together. So when we have a splitting of a parent that is black, in here we put 20 in. Well, we're going to move a 70 up so that we have no two reds together. So it's another variation of a tree used for various different problem solving. So now we put 60 in, 60 is red. It always comes in as red. We've got a problem again, so we got to rotate it or change the color. In this particular case, we just changed the 20 to red. We put 30 in, and we can move the 20 over, so we have two reds to a black. So you can see there's a very theoretical yet patterned type of construction. You do not have to work with red-black trees in this class either, just showing it to you in contrast with other types of trees. Don't want you leaving this class thinking that there's only a binary search tree. I do have some better applications. The red-black does come in handy for a few things. It doesn't solve a lot of problems. It is very, very specific to certain parameters. So I'm not going to go through the rest of this. I'm just going to show you what's here. It's like 80 slides and everything you want to know about red-black trees. But you can possibly see that the deletion as well is challenging. So I've run out of time. It's 9:15. Just leave it with that. This is an introduction to different types of trees today. So, all right. So you're gonna get some binary stuff for the asynchronous part of this week. And then just keep in mind that next week, I will be out of town. So we will not have a class meeting next Monday. I will be sending out a message and then we will also put a sign on the door so you remember. So have a great rest of your week. I'm not going to see you for 2 weeks. I won't see you next week, but I'll see you the following. But I'm also available by email as well in office hours. I just flying back on Monday, so. All right, have a good one. Start working on assignment number 2 if you haven't done it yet. So number 1 was due yesterday. Questions online before I disconnect? Nope. Okay, see you guys a couple weeks.